So welcome everyone to this webinar in the LIBREhub series. Today we have a guest, Dr. Darren Roblyer. He's an associate professor of biomedical engineering at Boston University. His research focuses on translational diffuse optical imaging and spectroscopy. His group develops both wearables and frequency domain near-infrared spectroscopy techniques to address unmet clinical needs in cancer, cardiovascular disease, and kidney disease. He received his bachelor's degree in biomedical engineering from Johns Hopkins University in 2004 and received his PhD in bioengineering at Rice University in 2009. So today we're going to hear about an open hardware project for label-free measurements of tissue optical properties. And with that, let's welcome Darren, and we're very excited for your talk.
Thank you, Vicente. Thank you for the invitation, and it's a pleasure and honor to speak to the LIBREhub community today. So yeah, I'm going to talk about a technique called spatial frequency domain imaging and a project we call OpenSFDI, which, as Vicente mentioned, is an open hardware project. And I hope by the end of this talk, I'll convince you, much like I'm convinced, that SFDI is a powerful label-free technology that has many untapped applications still. So here's the outline for my talk today. I'm going to start with the background and theory of this technique, spatial frequency domain imaging. And I'm going to talk about the OpenSFDI platform and how you could build your own device. I'll show you a few use case examples of the technique. And then in the second half of the talk, I'll talk about new developments. So what we're doing to extend SFDI, for example, into the shortwave infrared, a longer wavelength range that's opening up new opportunities and new applications, and I'll show you some of those. So please let me know if you have any questions or put them in the chat. I'm happy to take them during the talk or afterwards. So let's get started. So spatial frequency domain imaging. So let's start big picture here. So SFDI fits within a collection of technologies that we can generally call near-infrared imaging or spectroscopy. And these have been around for over 40 years. And probably many of you are familiar with some of these technologies. So for example, functional near-infrared spectroscopy, or FNIRS, is a technique where there's an array of near-infrared light sources and detectors on the surface of the brain. And this near-infrared light, which ranges between 600 and 1,000 nanometers, can penetrate deeply in tissue in some cases, sometimes centimeters deep. So we can use this light to measure functional activation in the most superficial parts of the brain. And we do that by looking at changes in oxy and deoxyhemoglobin, like the one shown in this plot. And this allows us to spatially localize functional activation in the brain without a technology like FDG PET or fMRI, which are much more expensive. It also allows for measurements to be taken while patients are freely moving or subjects are freely moving. Other examples include diffuse optical spectroscopy, DOS, or diffuse optical tomography. And there's been many applications over the years. One that's near and dear to my heart is measuring breast cancer patients while they're getting chemotherapy. So this is a picture from the Beckman Laser Institute, which is part of UC Irvine, showing a breast cancer patient getting scanned with a DOS probe. And from this probe, you can create maps that show contrast of the tumor. Here you're looking at increases in hemoglobin. And so near-infrared imaging in general has some advantages in that it's label-free, provides functional information in that it can tell you about changes in oxy and deoxyhemoglobin, and it can measure quite deep. And the fundamental contrast for these technologies is a combination of both absorption and scattering. So just a few definitions here, but you'll see this throughout the talk, but the absorption coefficient, which we call mu-A, has units of inverse distance. And the absorption coefficient tells us about the probability of absorption per unit path length. And if we take the inverse of mu-A, it tells us about the mean free path for absorption. So how far in tissue does a photon travel before it gets absorbed? And this is the same for the scattering coefficient, so the probability of scattering per unit length, path length. And the table here gives us a few typical values for the path length for mu-A and path length for mu-S. So in tissue, a photon travels between 10 to the power of 2 or 10 to the power of 4 millimeters before it's likely to undergo scattering. Much shorter path lengths, for absorption, much shorter path lengths for scattering. scattering is much stronger in tissue than absorption. You can also see this for time scales. So between absorption events, you can expect photon to travel tens of nanoseconds versus tens or hundreds of femtoseconds for scattering. But the idea here is if we can measure absorption and if we can measure it at multiple wavelengths, then we can use it to extract quantitative values of what we call chromophores, or absorbing species in the tissue. And examples of those are shown on the right. So oxyhemoglobin shown in the red, deoxyhemoglobin, lipid, and water. So the key is, how do we measure the absorption coefficient? Scattering coefficient can also serve as a biomarker, and sometimes we want to measure that as well. Okay, so Beer's law is what we use to extract tissue concentrations of chromophores. So here's Beer's law. It represents the relationship between the absorption coefficient, which is wavelength dependent, what's called the extinction value, which is also wavelength dependent, and the concentration of a chromophore like oxy or deoxyhemoglobin. So if one can measure mu-A at multiple wavelengths, as shown in the red dots here, a mu-A spectrum in the brain, and one can look up extinction values from literature, then you can solve for the concentration. And if you want to solve for 3 chromophores, then you need to take measurements at least 3 carefully chosen wavelengths. So again, how does one get to measurements of mu-A in tissue? So this actually turns out to be a little bit tricky to do this quantitatively. So if we look at the left part of this plot, what you're looking at is a laser beam incident on a cuvette. And in this cuvette, there's some absorbing dye. And as you go from left to right, there's increased scattering added to the liquid in this cuvette. So in the case of all the way to the left, where there's almost no scattering, it's quite simple to get at mu-A because we know the path length of these photons. Let's call it a centimeter for simplicity. One can use the Beer-Lambert law, which is the relationship between the light into the cuvette versus the light out of the cuvette. It's simply a function of mu-A and the path length of the photon, where we can use 1 centimeter for L. But as we move to the right, where things become much more tissue-like, we don't know L, we don't know the path length because the photons are traveling in a circuitous path. And therefore, the Beer-Lambert law becomes more difficult because we don't know the path length of the photons. Okay, so how do we deal with this? So there's a few different technologies in this area, and by far the most common is called continuous wave, sometimes called continuous wave diffuse optics. And FNIRS, which I started with, most typically use continuous wave, especially for commercial devices. And this is when we send a steady state light source into tissue and measure the attenuation. And the attenuation is going to be caused by both absorption and scattering. So here we don't have enough information to separate or measure independently absorption and scattering. So what groups do is they can assume a mu-S prime that's based on the part of the body they're measuring. And when you do that, you can either get absolute or changes in mu-A, and done at multiple wavelengths, one can extract oxy and deoxyhemoglobin or oxygen saturation. Now, if one wants to separately measure and quantify mu-A and mu-S prime, it's necessary to modulate the light source. So one can do this by modulating the light source in time. This is called frequency domain diffuse optics. And this modulation typically occurs at tens to hundreds of megahertz. And by measuring the amplitude and phase and using a model of light propagation, one can extract mu-A and mu-S. Or you can send a pulse of light into the tissue and look at what's called the temporal point spread function, or the smearing of that pulse as it comes out of the tissue. Again, sufficient information is contained in the shape of this pulse to extract mu-A and mu-S prime when used with a light model of propagation. And then when measurements are taken at multiple wavelengths, one can extract molar concentration or absolute values of oxy and deoxyhemoglobin. Let's briefly take a closer look at frequency domain and time domain techniques, because these will get us to the topic today, which is spatial frequency domain imaging. Okay, so in time domain imaging, what one is measuring is often called the temporal point spread function. So at the detector position, one's measuring light intensity and how it decays in time. And with a sufficiently short pulse, we're typically measuring this on the order of nanoseconds. If one takes a Fourier transform from this domain into the time frequency domain, we're looking at the temporal modulation transfer function. So here the response is a function of time frequency, typically for tissue in megahertz or sometimes gigahertz. And in theory, these two techniques contain the same information. Now it depends on the bandwidth of the time frequency domain measurement, but one can get the same information from these two technologies. Okay, so there's an analogy here. Let's now think of a different measurement geometry. It's called spatially resolved measurements. So think of an optical source fiber, and then a detector fiber that's moved further and further away from that source fiber on tissue. Here we're measuring light intensity as a function of distance from that source fiber, and this is called the spatial point spread function. So if one takes a Fourier transform of this spatial point spread function, we get into the spatial frequency domain. And here we're looking at the spatial modulation transfer function as a function of k, or spatial frequency. And in each case of these point spread function or modulation transfer functions, the shapes of these curves are dependent on the tissue absorption and scattering coefficients. And it's this modulation transfer function that forms the basis of spatial frequency domain imaging. So now I'll tell you how we actually take these measurements in the spatial frequency domain to extract mu A and mu S prime. I should also say that techniques like continuous wave, time domain, and time frequency domain have been around for quite a while, so several decades. There's fewer groups in the world that use time domain methods because it requires the electronics and timing electronics to get nanosecond timescales, and frequency domain requires measurements of amplitude and phase. But they're powerful techniques. Spatial frequency domain imaging, in contrast, has been around for much less time, really just the last 15 years. So there's still a lot of development that's going on in this area. So spatial frequency domain is fairly simple in terms of its measurements, at least in principle. So here we're projecting 1D sinusoidal patterns of light onto tissue. And what you're looking at is the back of a hand, the dorsum of a hand. And to do this, we can use a digital micromirror device or really any spatial light modulator. We illuminate the tissue over a wide field. So for example, one of our devices has a field of view of 15 by 20 centimeters. And then we simply collect the remitted light with a CCD camera. Now here we want to look at the diffusely reflected light. So we use cross polarizers, a polarizer here and a polarizer here. They're cross linear polarizers that are crossed with each other. And this rejects specular reflection. And what you're looking at is a progressive projection of low spatial frequencies. There's DC, and then high 0.05, 0.1, 0.2, and 0.4 inverse millimeters, or cycles per millimeter. And in order to build up that spatial modulation transfer function, one needs to measure at a minimum 2 different spatial frequencies, and sometimes more is better. So practically what we do is we take a DC measurement, so that's just planar illumination, and an AC measurement, meaning a modulation that's higher than planar. And here is showing examples between 0.05 and 0.4. And we're doing this we're not just projecting one pattern per frequency. We're projecting multiple shifted patterns, and that's so that we can demodulate the image. And I'll show you how we do that in the next slide. But after we go through a demodulation and calibration procedure, we can get diffuse reflectance maps, diffuse reflectance being defined as a value between 0 and 1. It tells us about light out of the tissue versus light in. We can get that at low frequencies and then higher frequencies. And already you can see visually that low versus high frequencies are telling us something different about the tissue. So these are measurements taken, as I mentioned, on the back of the hand, and you can see these superficial blood vessels. And you can see them quite a bit better at low spatial frequencies. And it turns out that low spatial frequencies are more sensitive to absorption, and progressively higher spatial frequencies are more sensitive to optical scattering. And then an inverse model is used to take these diffuse reflectance maps and convert them into maps of absorption and reduced scattering. And we have to perform the inverse model for each pixel in this image. And now we have optical properties. And if we take measurements at illumination wavelengths carefully chosen, we can then again use Beer's law to extract chromophore concentrations with known extinction values. So here, for example, if we take measurements on the back of the hand at 750 and 850 nanometers, which are wavelengths sensitive to deoxy and oxyhemoglobin respectively, we can get back oxygen saturation as well as levels of oxy and deoxyhemoglobin. Okay, so I'll talk a little bit more about the demodulation and calibration procedure here. So in this video, we're looking at projected patterns again on the back of the hand. And you're seeing for a given spatial frequency, we're rotating the pattern. And what we do is we project at 3 offset phases, 0, 2 pi over 3, and 4 pi over 3. And we illuminate with patterns. If you take a line profile through these 2D patterns, you can see in one dimension here what that illumination looks like. We illuminate the tissue, and then the camera measures the emitted light. And what we measure is a combination of that original sinusoidal pattern at the 3 frequencies, the 3 phases, as well as an envelope function, which we call MAC. And it's the envelope function that tells us about the frequency response of the tissue at that specific modulation frequency. And we want to extract this envelope. And one can do this relatively easily by taking these 3 projected images, or the camera versions, the camera collected versions of that remitted light, and putting it through a demodulation algorithm. So in DC, we simply add those 3 images and divide by 3. For AC, the algorithm is shown here for the cases of 3 phases. So you can see, for example, image 1 minus image 2 squared and so forth gives us that envelope function that we're looking for. So MAC is the spatial frequency response for a given position and given spatial frequency. So what we want to get at is the diffuse reflectance. What we've measured is MAC, or in the case of DC, MDC. Now we have to deal with the fact that there's a system response. There's a modulation transfer function of the device itself. So the diffuse reflectance is going to be a function of that system response and the initial illumination. And just a reminder, diffuse reflectance, again, scale between 0 and 1. How do we get diffuse reflectance? The typical way to do that is by using a calibration phantom. So there's many different kinds of phantoms used for diffuse optical imaging, but it's common to use something like this. This is an example of a silicone-based optical phantom. So as before the silicone cures, one can add an absorbing dye and a scattering agent. So examples of that are titanium dioxide is a good scatter for the near-infrared wavelength range, and nigrosin is an example of a good absorber. And so if we have a phantom like this where we know the optical properties, the mu-A and mu-S prime at a given wavelength, we can use a forward model to get to a known diffuse reflectance value at that wavelength. And so we can measure this phantom. We'll get an MAC for the phantom. We know what the RD should be. So now we have a mapping between our measurement and the known RD. We assume that mapping stays the same when we measure the MAC of something unknown, like tissue, and we can use that to get to the diffuse reflectance of the unknown of the tissue value. So this is key for SFDI. One needs to use an optical phantom with known optical properties. Okay, so that's how we get to this stage again, diffuse reflectance. Then one last step, the inversion. How do we do the inversion? So we have this case where we are taking measurements at 2 spatial frequencies. So we're sampling the spatial modulation transfer function. How do we convert those measurements into optical properties? So there's multiple ways to solve the inverse problem. I'll show you 3 different ways to do it. The earliest way people figured this out, and in some sense the simplest way, is by using what's called a diffusion equation. So this is an approximation that tells us how light diffuses through tissue. It's an analytical expression that can be solved in the frequency domain. So if one inputs the spatial frequency as well as mu-A and mu-S prime, what you get out is diffuse reflectance. And the nice part about this is it's very quick to solve. The part that's less pleasant is that it can only really be solved in the forward direction, meaning optical properties in, diffuse reflectance out. And that's exactly opposite of what we're doing, right? We're measuring diffuse reflectance and we want to get the mu-A and mu-S prime of the tissue. So one needs to wrap this in an iterative inversion model where one takes a guess at the mu-A and mu-S prime, compares it to the measurement. If we're below a certain error metric that's defined by the user, we stop. If not, we iterate. So this works well, but the issue with its use in SFDI is we have to solve it for every pixel in the image. And so this is how people who are working on early SFDI actually solve the problem, but it could take hours or days to get your maps of mu-A or mu-S prime. A much more efficient way to solve this problem is by using a pre-computed lookup table. An example of that is shown here. So on the axes are diffuse reflectance at DC and diffuse reflectance at a higher spatial frequency. These are your measurements, and they map to some unique mu A and mu S prime value. So in the lookup table, mu S prime are shown as isolines vertically, and mu A is shown as isolines that are mostly horizontal. So where your measurements meet mu A and mu S prime gives you the mu A and mu S prime of your tissue. And this lookup table can be pre-computed using the diffusion equation, or more commonly a Monte Carlo based simulation. And then doing this inversion is simply looking up in the table, which is very fast. Another way this problem can be solved is by using Monte Carlo results or an analytical model to train a neural network. And we showed how this could be done back in 2018. Here, the neural network structure is fairly straightforward, but the inputs are the diffuse reflectance at different spatial frequencies, and the outputs are mu A and mu S prime. And you can see this works very, very well if you're careful about the architecture of the deep neural network, and it's also very fast. So for example, if one compares in an image that's 100 by 100 pixels, the iterative method can take hundreds of seconds, whereas the lookup table can take about 1.7 seconds, and the deep neural network takes 0.005 seconds. So these methods are available and in the literature, and on the OpenSFDI website, we give some example code so one can try the inverse problem if you collect your own data with your own SFDI system. Okay, so just to emphasize that, we're taking measurements at a low frequency and a higher frequency. Those measurements sample the spatial modulation transfer function, and they also give us a position on the lookup table that tells us about mu A and mu S prime, and we do that for every pixel in the image. Okay, so what's giving us this differential sensitivity to absorption and scattering in SFDI? In the original paper on SFDI, which was back in 2009, and the full citation is shown here at the bottom of the page, they did an interesting experiment where they made liquid phantoms, where they could change the absorption and scattering of the phantom to simulate different types of tissue. So in this example, what they did is they kept mu S prime scattering constant, and they changed mu A over a wide range. And then they plotted diffuse reflectance as a function of spatial frequency. And each line shows the results from a single phantom. So absorption is increasing as we go down the page. And what you'll see here is that at low spatial frequencies, there's a lot of difference between the diffuse reflectance, this is your measurement, when you change mu A, whereas at high spatial frequency, there's very little. So this tells us that, again, low spatial frequencies are sensitive to changes in absorption or absorption in tissue. Now they conducted the exact opposite experiment where they kept mu A constant and changed mu S prime over a wide range. And here you see the diffuse reflectance changes less at low spatial frequencies and a little bit more as you get to an intermediate spatial frequency. So higher spatial frequencies are more sensitive to changes in scattering or scattering in tissue. So the choice of spatial frequency in your measurement is an important one, and also comes with some nuance. So for example, this is from a paper we published in 2016, and it's visualizing the lookup table that one would use for different choices of spatial frequencies over a range of optical properties. So here it's very common to use DC or planar illumination as your low spatial frequency. And DC was paired with progressively higher second AC spatial frequencies. And so there's an issue when one chooses a second very low or very high spatial frequency. You can see that the mu A and mu S prime isolines, they collapse on top of each other as you use a very low spatial frequency. And so that means for a small error in your measurement, this can map to a large uncertainty or error in your extracted optical properties. Same down here, although the shape's a little bit different. You get compressed in this lookup table in the higher spatial frequency. Again, just meaning a small difference or noise in your measurement can lead to large uncertainties in the optical properties. So for most groups at most times, using some intermediate second spatial frequency, and 0.1 and 0.2 inverse millimeters are very common, gives us a more orthogonal lookup table with lower uncertainties in the extracted optical properties. And I had a postdoc that wrote a paper about this, again back in 2018. And what she did is she looked at combinations of DC with a second spatial frequency, and that second spatial frequency is shown on the x-axis. And what you're looking at in the plot is the mu-a uncertainty, and the uncertainty that's caused simply by the inverse model lookup table. And each bar, each color in the bar, is showing a different theoretical tissue optical properties. And we looked at low mu-a, low mu-s prime, low mu-a, high mu-s prime, high mu-a, low mu-s prime, and high mu-a, high mu-s prime. You can see the uncertainties are minimized over these optical properties when one, again, uses an intermediate second spatial frequency around 0.1, 0.15, or 0.2. And this is, in fact, what most groups do unless they're doing something really particular with SFDI. Here's an example of what happens when you choose what I'll call a more favorable choice of frequency pairs versus a less favorable choice. What you're looking at is chromophore extractions, oxy and deoxyhemoglobin, from a cuff occlusion. So blood pressure cuff is put on the upper arm, and then SFDI was used to measure the lower arm. And during the occlusion, where you're blocking arterial supply, there's a drop in oxyhemoglobin, an increase in deoxyhemoglobin, and then reactive hyperemia that occurs after the cuff is released. And you can see when we use 0 and DC, these patterns are very clear. But when we use 0.05 and 0.1, so these are two spatial frequencies that are too close together, we can still see the changes, but there's much more uncertainty. And any noise in the measurement, which there's inevitably going to be in a physiological measurement, causes us to have a large overlap between the oxy and deoxy, and just the clarity of our signal is greatly decreased. Okay, so with that, I'm concluding the first part of my talk where I'm talking about the fundamentals of SFDI. And I want to show you a little bit about what can be done with this technique now. So in this slide, what I'm showing you is an array of examples of different applications for SFDI that my group and other groups have used. And I'll take you through a few of these. So for example, in the preclinical setting, my group has used SFDI to track small animal oncology models. So these are tumors that are grown subcutaneously on the back of mice. And we can track oxy and deoxyhemoglobin or optical scattering as animals are treated with different types of cancer therapies. So in this case, it was an antibody-based therapy and a cytotoxic therapy. And we can see large differences between these groups. So this is to help us understand how these tumors are responding to treatment in the functional way, as well as related to the microarchitecture of the tumor when we measure scattering. And it helps to inform some of the studies we do in humans with breast cancer patients. Here's a totally different example, also in mice, but looking at the brain with the skull thinned. And here we can induce a stroke with damage caused by a laser. And optical scattering tells us in the first few hours after inducing that stroke where the boundary of that stroke damage is. And this is a project we did in collaboration with the BOAS lab, which is also here at Boston University. Now, Brian Poe's group, who's at the University of Wisconsin in the United States, has used SFDI, especially high frequency SFDI, to look at breast tumor margins. So these are resected lumpectomies or tissue from breast cancer patients. And the idea here is one wants to identify if there's residual tumor in the boundaries of this resection. And so they looked at scattering signatures from SFDI to try to identify and classify different tissue types, like adipose, fibroglandular, and invasive cancer. The company that's commercialized this technology, it's called Modulum. It's based out of Irvine, California, is using this technology to look at diagnosis and prognosis of diabetic foot ulcers. So in the case of diabetes, it can happen that because of reduced blood flow to the feet, patients can develop diabetic foot ulcers in the bottom of their feet, and which are very difficult to treat because they heal very slowly or not at all. And so the idea here is if you could predict who's at risk or who's going to develop a diabetic foot ulcer, this could help you intervene earlier to help these patients. And so here they're using SFDI at multiple wavelengths to look at the tissue oxygen saturation in the skin of the foot at more superficial and deeper vascular beds. And one can see, compared to a patient with no diabetes, someone with diabetes has less total hemoglobin, someone with diabetes plus neuropathy has even less, and someone with diabetes, neuropathy, and retinopathy, meaning they have much more severe cardiovascular disease, has even less total hemoglobin in their foot, and they're more at risk for developing diabetic foot ulcers. And then one last example here. So a student in my lab is pursuing a project related to a disease called scleroderma. So scleroderma is a skin disease where fibrosis builds up in the dermis. It also builds up on internal organs of the body, like the lungs, so it can be fatal. And here we used SFDI to measure the hands, but also the arms of patients. And we're looking at a comparison between a healthy control in white light and someone with scleroderma. And what we found is that the mu-s prime, the scattering, in the subjects with scleroderma is substantially less than the healthy controls. And so now we're exploring this SFDI as a tool to help diagnose this disease and to track these patients as they're receiving therapy, to try to understand whether their fibrosis is getting better or worse. And this could be a powerful tool, for example, exploring new drugs in the pharmaceutical industry that are meant to treat scleroderma. So I hope that gives you a little taste and flavor of what's been done so far with SFDI. But because of the strengths of the technique, the fact that you can quantify optical properties in chromophores, it's clear to me that there's many other applications that have yet to be explored. And hopefully some people listening to the talk will have new ideas of how to use SFDI. And if you do, we have a resource called OpenSFDI that is basically a step-by-step procedure on how you can build your own SFDI system, an LED-based 3-wavelength system. So this was spearheaded by a postdoc of mine, Matthew Applegate, a few years ago, but it was also in collaboration with a few other universities, the University of Maine, the Neurophotonics Center here at Boston University, Linköping University, as well as the University of Strasbourg. And I'll just show you the website briefly to give you a sense of what's contained there. So if we go to the website, which again is just opensfdi.org, the first thing you'll see is SFDI 101, and it actually goes through some of the basics of what I just talked about. The spatial modulation transfer function gives you a list of SFDI references and some of the core references. And then I'll take you through materials, and I won't go through this whole thing, but I'll just show you a few examples. So this is a 3-wavelength SFDI system. If you build the whole thing, it'll cost you about $4,700, although, and this is US dollars. If that's too expensive, there's ways to get around this, right? The most expensive part is the digital micromirror device. And one can use actually a projected or a printed pattern, a transparency, if you're only interested in looking at information at one spatial frequency. But here's the breakdown of the cost. But if one clicks on one of these, for example, in the optics, it'll take you to specific lenses, the vendor, the part number, and then a link to that part, as well as the cost. And so this can be useful. We update this as much as we can. Some of this needs to be updated. The DMD from the supplier, they're starting to change their part numbers, but you can still get the DMD that we use for this project. And then importantly, through the assembly, we take you through part 1, putting the optical components together, mapping out the spatial paths, the LED alignment, the projected alignment, and imaging itself. We take you through acquisition. For acquisition, we use LabVIEW, but one can use whatever programming language you like. We give you an example of a LabVIEW interface, which we use to control the SFDI system. And then we take you through the processing. And there's a really nice processing tutorial that was put together by a guy named Rolf, who's a professor in Sweden, who takes you through the demodulation, gives you some MATLAB pseudocode on how to process the data, some debugging when you have demodulation errors, really, really nice tools. And then finally, in the processing, we have this thing called App SFDI. And this is an application where you can take raw data and convert it using the inverse model into optical properties. And then there's a blog about experiences different groups have had and any problems you can post there. So we hope that that's a useful tool. And we know that multiple groups around the world have used this website to build their own SFDI systems, and some of which are published. So please take a look if you're interested. And then with my remaining time, I just want to tell you a little bit about what's new with SFDI. So the technique, as I mentioned, has been around for about 15 years. And by far, most groups have used it to measure visible and near-infrared optical properties in chromophores. So what we're doing with SFDI is taking it from this wavelength band and starting to extend it out into what's called the shortwave infrared. And the shortwave infrared is doesn't have one strict definition, but for the purposes of this talk, we'll say it's between 900 and 2000 nanometers. Now, some groups and some research will call this the near-infrared 2 window, or even sometimes parts of it the near-infrared 2B window. But the tissue optical properties are quite a bit different in the shortwave infrared compared to the near-infrared and visible, and I'll show you more about that in the next few slides. But one important feature is that oxy and deoxyhemoglobin, which are shown in red and blue, are much less dominant in the shortwave infrared, where lipid and water become the dominant absorbers. And because of some of the advantages of the shortwave infrared, as well as the increased availability of detectors in this wavelength range, the number of publications related to shortwave infrared and shortwave infrared imaging has gone up at a pretty nice pace over the last 20 years. So I consider it to be an exciting area that's currently underexplored. So if one looks at a few examples of optical properties in tissue and compares the near-infrared wavelength band to the shortwave infrared wavelength band, and here you're looking at brain, breast, and skin as 3 examples, one can see that the absorption overall for tissue tends to be quite a bit higher in the shortwave infrared, but the scattering tends to be quite a bit lower. And these 2 trends can be used to one's advantage. So for example, for groups that do exogenous fluorescence imaging, which is not us, but for groups who do this, they found that moving to longer wavelengths can help them get higher resolution images deeper in tissue. So this is an example of a group that's imaged the brain through the scalp, and they're using emission wavelengths in the near-infrared 1 window, and then out here into the shortwave infrared, which they call 2 and 2B. And if you look at this large vessel in the brain, the signal to background ratio increases when you move to longer wavelengths. And this is a combination of the fact that absorption is about 11 times stronger out here at 1600 compared to a near-infrared wavelength of around 875, and scattering's 3 times weaker. So less scattering means less blurring, right? Your photons travel in a straighter path, but absorption, paradoxically in some sense, actually helps you here as well, because longer path length photons, which tend to be photons that scatter more, are going to be much more likely to be absorbed in this highly absorbing tissue. So this combination of low scattering and high absorption, as well as lower autofluorescence at longer wavelengths, can lead to better images like this. Now there's a caveat here. One needs to be able to detect a small number of photons that are making it from these deep depths. In order to do that, you need quite a sensitive detector and a fluorescent dye that has sufficient concentrations with a large quantum yield. Now, if one's not doing fluorescence, and you're looking at endogenous imaging like my lab does, there are still penetration benefits under some circumstances. So what you're looking at here are the 50th percentile photon penetration depth for the case of planar illumination in these same 3 tissues over a wide range of wavelengths. And this data is from a series of Monte Carlo simulations that were conducted in collaboration with Vasan Venugopalan, who's at UC Irvine. And so what you see is at 1100 nanometers, there's a penetration window advantage where you can image deeper than the visible or near-infrared, sometimes by up to about 1 millimeter. And depending on the application, this could be a substantial advantage. And this window around 1100 exists because water and lipid have a local minima, causing local minima in the mu-A, whereas scattering is also decreasing. Now, past 1100, there's just too much absorption from water, and you start to lose penetration depth again. But I'll come back to this 1100 nanometer later in the talk, because it's a useful wavelength. Now, there's also some challenges in shortwave infrared imaging, maybe most notably the fact that silicon detectors lose their quantum efficiency around 1,050 nanometers at best. So you need a different detector semiconductor material, typically germanium or InGaAs are the options there. There's an issue here though. The band gap energy for germanium InGaAs is about half that of silicon. That means that thermal effects can cause electrons to move up to the conduction band. This just leads to dark noise, thermal noise. And the way that's combated is by cooling the detector, sometimes to very low temperatures, like in the case of this Princeton Instruments InGaAs detector to minus 200 degrees centigrade, which reduces dark counts by several orders of magnitude. Other challenges include regulations around use of SWIR cameras. So in the US, these are called ITAR regulations, and you may have similar ones in different Latin American countries. So this is for defense reasons, it's sometimes difficult to use these cameras. Also, the optical sources, the optics, there's just less availability and costs can be higher. So you can imagine for these detectors where you're cooling, it's just a more expensive camera. So a scientific grade InGaAs camera can cost somewhere between $10,000 and $30,000 or $40,000 these days, although prices are coming down dramatically as more and more companies start to make these cameras. Other challenges include the models we use to understand how light propagates through tissue. So I mentioned this earlier in the talk, but it's quite common in the near-infrared wavelength range to use an analytical model of light diffusion. But one of the assumptions for this model, because it's an approximation, is that scattering is much higher than absorption. So if one compares diffuse reflectance for brain tissue from an analytical model versus the gold standard Monte Carlo, they match pretty well up to about 1,000 nanometers, and then they start to diverge. Looked at in a different way, the black line here is showing the ratio of mu s prime over mu a. And one that dips below 10, which is the assumption for the diffusion approximation, the diffuse reflectance error, difference between Monte Carlo and the analytical model, gets a lot higher. So all this to say that when imaging in the shortwave infrared, it's much better to use a Monte Carlo based model than an analytical model. And this leads to more computational costs, but fortunately there's a lot of actually open software solutions for doing Monte Carlo based simulations these days. Okay, so just to review shortwave infrared, some advantages are improved spatial resolution and imaging depth for exogenous imaging. And in certain cases like the 1100 nanometer window, there's improved penetration depth for endogenous imaging. I didn't have time to talk about this, but the shortwave infrared also has lower sensitivity to melanin. And this can, of course, be useful for imaging a range of subjects with different skin tones. And then there's this differential sensitivity to water and lipid. And these advantages have led to new application areas being explored, like hydration, edema, volume monitoring. This is volume monitoring refers to the amount of water in a person's body. Body composition for sports medicine, and then applications in cancer and heart disease. And if you're curious about how the groups are using shortwave infrared, you should check out a special edition of the Journal of Biomedical Optics that's coming out in September, that's co-edited by myself and Mark Pierce at Rutgers and Daniel Fried at UC San Francisco. It's a nice collection of papers where different research groups are using shortwave infrared imaging for a number of different preclinical and clinical applications. Okay, so combining these ideas, SFDI and the shortwave infrared, we designed a hyperspectral system where we could take measurements that span the near infrared and we could compare them to the shortwave infrared. And we built this system that's based around a tunable laser. And this tunable laser is a laser we had for multiphoton imaging in the lab. It ranges from 680 to 1300 nanometers. So we can explore the near infrared and then the first part of the shortwave infrared, which is really where a lot of the action occurs. Past 1300, again, absorption is so high, you really can't penetrate very deeply into tissue. And the output of this laser, we sent through a diffuser, we collimated it, put it through a linear polarizer. Here's our digital micromirror device that we use to then project spatial patterns. And in this case, we collect with a germanium dose CMOS camera that has spectral sensitivity over a wide wavelength range up to 1600 nanometers. And with this, we could collect hyperspectral data cubes. So here's an example of a liquid phantom we measured that has intralipid on the bottom. Intralipid is a soybean oil emulsion. And on top is pure soybean oil and then a drop of blood. And in these hyperspectral data cubes, one for near infrared and one for the shortwave infrared, one can see spatial dimensions, an X and Y, and then wavelength dimension. And the color indicates mu A, the absorption coefficient. And the near infrared, you can see that drop of blood very nicely, but you don't really see the oil. But you do in the shortwave infrared because lipid is so absorbing here. So this is just, I think, a nice way to show the differential contrast between these two wavelength bands. And then we can take those data cubes and use Beer's law again to extract 2D maps of chromophore concentrations. In this case, oxime deoxyhemoglobin, since that drop of blood is exposed to air, all of that hemoglobin is oxygenated. And then there's water throughout the phantom, and then there's higher concentrations of lipid where that oil slick is, where that soybean oil is. Okay, and then we took this device and tried it in a number of different applications to really show what could be done in the shortwave infrared if one has a quantitative technique like SFDI. We looked at edema. So here what we did is in a mouse, we injected either PBS under the skin, this is non-inflammatory, or a chemical called TPA, which does induce inflammation, which we proved by increase in white blood cells. And so that inflammation causes vessel leakiness and more fluid to accumulate around the injection site. And these are maps of water concentrations shown 2 hours after the injection. You can also look at this longitudinally. So for the mice that were given PBS, there's an increase in water after the injection that then dissipates as that water is, or the PBS is absorbed by the tissue. But in the case of the TPA, that inflammation causes edema, so that amount of moisture increases over time. So this could be useful for measuring a number of diseases in the skin that induce edema and inflammation. And there's really very few ways to quantitatively monitor edema that are available in the literature. So this is one example. We also looked at the quantification and mapping of lipids, in this case, a tumor. So we grew tumors in mice, we excised them, cut them in half, imaged with SFDI, and then we did histology as a gold standard. Here's an example of one of these tumors. We can map lipids throughout the surface of this cut section, and then different locations we can do oil redo staining, which is the gold standard stain for lipid concentration. And over a number of tumors, we can see a nice correlation between the optically measured lipids versus the lipid fraction from histology. And so spatially mapping lipids like this could have potential applications for chemotherapy monitoring, for tumor margin detection, or for just understanding the composition of the body over different locations. We call that body composition measurements. And then I'll just finish up with one more application, one I'm really excited about. And so here we're using near and shortwave infrared SFDI for blood lipids monitoring. So by blood lipids, I mean the amount of triglycerides and cholesterol in your blood. So triglycerides and cholesterol are some of the most important and most used biomarkers in all of medicine. And it's because they strongly predict future cardiovascular disease, things like myocardial infarction, heart disease, stroke, and death. And the standard of care is you do a blood draw, and then you do traditional chemical assays to get the concentrations of triglycerides and cholesterol. So we asked, could we envision a future where we optically monitored levels of triglyceride and cholesterol using optical techniques? This would have potentially large impacts in terms of risk prediction, diagnosis of cardiovascular disease, for therapy monitoring, and for management of dyslipidemias like type 2 diabetes. So in order to tackle this problem, we first focused on a certain scenario that's been well studied in this area, and it's called postprandial state. Postprandial simply means after a meal. And after one eats the meal, it's perturbing the system. One can track the level of triglycerides after that meal. And they peak around 3 hours after a high-fat meal. And the time course of these changes is different depending on whether you have cardiovascular disease or not. So in this study, they showed through serial blood draws that patients with prior heart attacks had a higher increase in their triglycerides for the same meal. And those triglycerides stuck around longer in the blood. This is bad when the lipids stick around longer in your blood because they actually end up attaching to the inside of your blood vessels, causing atherosclerosis. And so we asked, how could we measure these triglycerides optically? There's at least two different ways we thought about this. First is through optical scattering. So these triglycerides are contained in micelles, so they can travel through the blood, which is mostly water. And these are naturally made nanoparticles that can be as large as a micron. And so what's shown here is an example of simulated plasma with more and more triglycerides. You can see this has a milky effect at high levels. And this is because there's a large amount of scattering. And we can measure scattering with SFDI. Now, I won't have time to tell you the story about blood scattering, but we just published a paper on this a week or two ago that came out in JBO. So I encourage you to take a look if you're interested. But I'll show you today about the hemodynamics. These blood lipids can also cause changes in the superficial vasculature. There's been some prior literature related to changes in blood flow and endothelial function. So what we did is we had subjects come after fasting for 10 hours into the lab, and then we gave them either a high-fat meal of 60 grams of fat or a low-fat meal of 2 grams of fat. And we had 10 subjects in each cohort. And then we measured them every hour for 6 hours, the first measurement being at 0 hours, the baseline. And we measured the dorsum of their hand with SFDI, a combination of near-infrared and shortwave infrared. You can see examples of those measurements here. Now, as opposed to the prior slides I showed you, here we're just looking at a few individual wavelengths using LEDs. We also did a reactive hyperemia experiment using an arterial cuff occlusion. I won't show you those results today. But the third thing we did was take a blood draw. So this is the gold standard, so we could get gold standard triglycerides, cholesterol, and glucose. And what we noticed is in patients that had a high-fat meal, so here's an example. So triglycerides started at 45 milligrams per deciliter. 3 hours after the meal, they had spiked at 115 milligrams per deciliter. The amount of oxyhemoglobin in the dorsum of the hand increased dramatically, whereas for subjects that had a low-fat meal, we didn't see this change. In some cases, the hemoglobin even decreased. So looking at that in a different way, here's two optical metrics. This is oxyhemoglobin, and this is a composite metric of μA, the absorption coefficient at 880 nanometers times 1100 nanometers divided by 730 nanometers. And remember, this 1100 nanometers is that deep penetrating wavelength I talked about earlier. And so what you can see in the 10 high-fat patients, there's a peak that happens in this optical metric at 3 hours. And it's a very different trend compared to the low-fat meal subjects. This also occurred in oxyhemoglobin. And if we compare to the blood triglycerides, the gold standard, we can see that these trends are similar, showing that these optical metrics are tracking what's happening to the blood triglycerides, which is really exciting. We trained a SVM regression model using 5-fold cross-validation, using just this single feature, optical feature, and using 1 point of calibration for each subject. And here we could get measured triglycerides tracking very closely to predicted triglycerides with the machine learning model. And we could take those machine learning models and actually show how the gold standard triglycerides through the blood draw tracked with the predicted triglycerides for both the high-fat and low-fat meal. And so we're really excited about this result. It's telling us that optical properties measured in the skin might be able to tell us about the triglycerides without invasive blood draws, or at least without serial blood draws. And what's interesting about this is that the 1100 nanometer shortwave infrared wavelength really did provide the best prediction when we included it in the composite metric. And that may be a combination because of the deeper penetration. And it may also be giving us information about hemoglobin. Now, even though hemoglobin 1100 is overshadowed to some degree by water and lipids, it still has strong absorption. Okay, so that's an example of how near and shortwave infrared imaging can be used. I've showed you a few of those over the course of the talk, and I'll just finish by summarizing. So I started the talk basically with a tutorial And I hope I convinced you that SFDI is a powerful tool for quantitative and label-free imaging, with the caveats that the application you're looking at requires wide field imaging. The penetration depth is on the range of millimeters, so keep that in mind as well. I also showed you the OpenSFDI website and gave you some tools on how you could make your own device. And then in the second half of the talk, I talked about the shortwave infrared wavelength band and how that's providing some exciting new contrast and opportunities for medical imaging. And then I showed you how to combine these two ideas, shortwave infrared imaging and SFDI, and how we're using that to explore edema, tumor imaging, and most recently, non-invasive blood lipid measurements through the skin. So I'll just acknowledge the many people who have contributed to this work, especially the students and postdocs shown in bold here. So Matt, as I mentioned, spearheaded the OpenSFDI project. Jan Yu spearheaded a lot of the SWIR SFDI results I showed you. Vivian, who's a former postdoc, looked at some of the choice of spatial frequencies for SFDI. And then Anahita and Sam, who just graduated from the lab, really looked into the blood lipids as well as some of the differences in tissue optical properties in the near infrared and shortwave infrared. I also thank our collaborators and funding sources, and I'd be happy to take any questions if there's any now, but also feel free to email me. I didn't include it here, but you can get in contact with me by looking up the Bot Lab. My email address is simply my last name, Roblyer @bu.edu. So thanks very much for your time and attention, and I'll stop it there.
Fantastic. Thank you very much, Darren. This has been a really nice tour, really going from the basics of the tutorial, as you said, explaining what properties are you getting here and the interaction of light with tissue, and then up to the very latest advances you're spearheading and some of the clinical applications. So that's very interesting. Thanks a lot. So yeah, I think we can do a few questions, and so I have at least some questions related to clinical applications and also to technical areas. So maybe I can start with the first of those. So I'm having in mind two clinical applications that you didn't mention. So maybe I'll just throw them out there, and you can say if you see potential or if you know of other implementations that use this technology. So one of them is using optical tissue property mapping for assessing the liver fat contents. Mm-hmm. This could be useful in procurement of organs or transplant, for example. Mm-hmm. And another one I have in mind is looking at the time course of the capillary refill time. This could also be used for example, for assessing the chances of going into shock for patients in ICU in hospitals. So have you worked with any of those applications?
So I haven't worked directly with those applications. I can say just a little bit about them, although I don't know the details of the liver transplant. But I'll just say the things to think about, right, are if you want to assess the lipids in the liver, is it necessary that you measure deep into the liver or superficial in the liver? And is it necessary that you spatially map those lipids, right? So answering those questions will give you a sense of whether SFDI might be the right technology for that. If you have to get below maybe the first few millimeters, then there's other possibilities there. You can still use maybe shortwave infrared light, but SFDI just, it's limited to superficial measurements. And then for the capillary refill, that's a really interesting example. So there, capillary refill, I assume you're talking about like on the fingernail?
For example, yes.
Yeah, for example. So you need to measure relatively quickly, right? So one of the potential limitations of SFDI is that we take these sequential measurements, right? We project different spatial patterns, and then we have to collect an image at each one of those spatial patterns. And that can take time, but groups have come up with ways around that. So for example, there's what's called a snapshot method, where you project one spatial pattern, leave it projected, and then collect rapidly with the camera. And from measurements from that one spatial pattern, you can collect both DC and AC spatial frequency content. One way to do this that's kind of easier to think about is by doing line by line Fourier transforms from the image. And from each of those Fourier transforms, one can segregate the DC component and the AC component, and then use that for the traditional SFDI processing. So with that, you can go, hertz or even tens of hertz or faster. So that's one way you might get the time dynamics you need to see that capillary refilling, which if I understand correctly, I think it happens over the course of a few seconds. Is that right?
That's correct. And actually that leads nicely into my technical question that I had, because as you mentioned, right, I seem to understand there's a fundamental limitation here that you need to collect a series of patterns to then calculate one whole picture of the optical properties, right? And so if you wanted to image a fast dynamic process, well, on the one hand, I wonder how relevant is that? I mentioned the capillary field time. I don't know if there are any other processes that may be fast that you wanted to image. But then, right, what would be the, so it sounds like in every picture you're collecting part of this information, right? And there can probably be some assumptions that the scattering properties, let's say, for example, they may not change as fast as some of the dynamics that you're capturing, stuff like that. So I wonder if there are optimal ways to measure the whole range of optical properties without compromising on having to, let's say, do spatial averages or use a limited set of frequencies as the examples you mentioned.
Yeah, so I'll give you a few examples of maybe faster dynamics and how we've dealt with it. So for example, in the last study I talked about, we did these cuff occlusions, right? And the cuff occlusions, the occlusion can last several minutes. We typically do 3 minutes, but then when you release the cuff, the reactive hyperemia happens really fast, like in a few seconds, and the hemoglobin changes are large. So what we do there is something that you alluded to. We'll take an initial SFDI measurement to map out mu A and mu S prime, and we'll just take that slowly at the beginning. And then we'll assume that over the course of this measurement, scattering doesn't change. So then we can take rapid planar illumination patterns, measurements, and then since we assume scattering doesn't change and we know scattering, we can still extract quantitative mu A very rapidly. So all we have to do now is switch between two LEDs and take two measurements with the camera, just planar measurements with no DMD involved. So if you're in a case where scattering is not changing, that's something you can do, and it works quite well. And then in the case of if scattering is changing, like for the stroke example I showed you in the brain, if you're looking at something fast like that, in that case, that happened over a few hours, but if it's happening faster, then something like the snapshot method might be useful. Or, one of the things we've been doing is it's nice to come all the way to optical properties, but you could stop earlier. You could just look at diffuse reflectance maps. Remember I showed you that diffuse reflectance at higher spatial frequencies are basically telling you information about scattering. So, or at least you're going to be much more sensitive to changes in scattering. So in order to get those diffuse reflectance maps, again, you can use a snapshot method. You have to collect less data. You don't even need the inverse model. And that's one way you can kind of speed up the whole pipeline.
Very nice. So Tobias, I wonder if you have any question more on the specific open hardware side?
I do, both on the hardware and technical side. Thanks a lot. It was really interesting. So I did not know about this method before. So I think it's really nice. I mean, one thing that I think you have explained, but maybe I just reiterated because I thought it was interesting, so that you can, with this technique, if I understand correctly, you can distinguish a different scattering regime. So especially between me and Rayleigh scattering, you can tell the difference quite well. I guess that's, I imagine, so I work more with bacteria. I look at the microbiome. And so that could also be interesting because the bacteria themselves scatter highly in the sort of me scattering regime, but they might also have pigments and other components that absorb in the range that you're looking at. And related to that, I was wondering if you think you could distinguish between saturated and non-saturated fats, the infrared regime.
So let me address a few of those items. So just to be clear, we can measure scattering, and typically the output is the reduced scattering coefficient. Now, the scattering in tissue can be caused by me scattering or Rayleigh scattering. But we can try to deduce what's causing the scattering in tissue by the wavelength dependence of scattering. But we don't have a way of saying, okay, this is caused by Rayleigh versus this is caused by me, a direct way through the measurement.
Okay, but the wavelength dependence is quite large. I guess the difference between those two methods. So then
Yes, exactly. Yes, exactly. So that's scattering. Now, in terms of the bacteria, and in terms of application, this is an important point. So this technique requires that you're measuring in a diffusive or nearly diffusive media, right? So you have to be in the multiple scattering regime. And so you need to be a little bit careful when you're imaging small samples. So for example, we measure pieces of tissue, we want them to be at least a few centimeters by a few centimeters by a few centimeters in 3 dimensions, so that as the light enters and leaves the tissue, it's undergoing multiple scattering, and you can also get edge effects. You don't want the photons to leave the edge of what you're measuring. That will cause aberrations and inaccuracies in terms of the optical properties. So if your bacteria are in a culture or in a 3D material, that might work. If they're just in a petri dish, this might not be the right technology for that.
Okay, thanks. That's really great to know. Yeah, related to the hardware documentation, I just have one question actually, because I looked at your website, which was really nicely organized, but I couldn't tell at first sight, what's the license under which you release this information and images?
Yeah, so good question. And maybe I'm not answering directly because I haven't thought about it in a few years. So I don't want to give you the wrong information. Maybe we could talk about it offline. Is that okay?
Good to know. I mean, maybe if you dig it out again, maybe you can just add that on the webpage.
Yeah. That's a great point.
Clarify things for people.
Sure.
Especially if you make a version of it, or you make some changes, it's kind of important if you have a share alike license that people use the same one and so on.
Yeah,
so
exactly.
Important to know.
Yeah, good point.
But it looks great. So thank you very much for sharing this with us.
Yeah, of course. I really appreciate the opportunity. It's nice to talk to you.
Yeah, so I think
as Vicente mentioned, we always get quite a few YouTube video views afterwards. So I think that the major audience is not here with us now, but will be online later. So
okay, great. Sounds good.
That's fine. I think with some of these questions, we covered a bit of the different topics that relate to this talk and to our seminar. And so I just want to thank you again, Darren. This was a very nice chance to learn about your work. And so thanks so much for joining our webinar. Yeah,
thank you very much. And happy to be part of the LIBREhub project. And I wish you all the best.
Good. Thanks.
Thanks.